Greetings. I am Akhilesh Aditya, a junior undergraduate pursuing my computer science degree from BITS Pilani, Goa. I am here to present a paper titled Ocean towards developing an opportunistic continuous emotion annotation framework. Affective computing, a technology that senses the emotional state of the user and then responds accordingly. At the core of this technology lies the annotation of the user's emotional state. The ground truth labels used here are collected using the human-based annotation self-reports. These labels are then used for various purposes such as datasets, live usages, and ML models, and lots of other things. But the collection of these datasets using self-report is generally done post-interaction or post-stimuli. That is, after either watching the video, listening to audio, or any other activity. This leads to an issue though, the loss of intra-video cellular nuances. To deal with this, researchers came up with a new form of annotation, continuous annotation, where the user has to continuously annotate his or her emotional state. Even though this fixed the issue of intra-video nuances, it created a lot of other challenges, such as the added strain on the user, the degradation of viewing experience, as well as loss of immersion. These challenges are important to address as they contribute towards the user's emotion and hence it affects the direct quality of this dataset. So, we see that there is a need for an annotation approach to capture the emotion with respect to intra-video nuances without or with minimal disruption of the viewing experience. This leads us to our problem statement to develop a new framework for emotional annotation that captures the intra-video nuances and at the same time reduces the number of probes. In existing literature, continuous datasets are used to capture the subtle intra-video nuances. One such dataset is the open access dataset called CASE, the continuously annotated signals of emotions. As you can see in the picture, the users had to input the annotations using a joystick. The users were shown videos and they had to continuously annotate emotions using the joystick. These users were connected to 6 physiological sensors: the ECG, BVP, GSR, RSP, SKT, and EMG. The circumplex model is a model of emotion that represents human emotions in two parameters: valence and arousal. The 2D axis of the joystick was used to measure the arousal and valence in the case dataset. This dataset was created with the help of 30 participants to whom the 8 videos were played in randomized order. These 8 videos chosen were from 4 different categories with different emotional stimuli, namely amusing, boring, relaxing, and scary. These emotional stimuli were chosen in such a way that they cover all the 4 quadrants of the circumplex model. Now, coming to the key intuition behind the proposed approach. We know that emotions change slowly as they have a residual effect. By exploring the dataset, we can easily see that these changes are reflected by the physiological signals. Measuring these changes would allow us to probe at an opportune moment, and these probes would allow us to grab the inter-video subtle nuances with minimal number of disturbances. So basically, what we need is opportunistic annotation instead of continuous annotation. Now coming to the Ocean framework, the entire framework can be divided into 3 stages: segmentation, detection of probing movements, and its optimization. Starting with the segmentation, first we start with the physiological signals. In this case, by choosing the window size, in this case we have chosen the window size of 5 seconds. We segment this into by fixed window sizes. After this, we then compute the change point scores for consecutive windows. We use the RELSIF algorithm, which is based on density ratio, to calculate the change point score. Change point score is a mathematical measure of the relative change in the physiological signals. Next, we eliminate the lower end outliers as they correspond to points with minimal changes. We retain the higher end outliers on the other hand because as they specifically correspond to points with higher changes, and this is what we want. Now, for the remaining points, we perform k-means clustering with k equal to 2. Why 2? Because we intuitively want to see the probing moments versus non-probing moments. And we choose the probing moments by choosing the centroid with the highest score. Once we have the probing centroid, we choose all the moments with change point scores greater than the centroid score. We combine these change point scores along with the outliers that we retained over here to finalize the final set of probing moments for emotional annotation. Now, coming to the results, one question that naturally arises is what is the reduction in the number of probes? We can see that our R framework, Ocean, reduces the number of probes by 89% on average when compared to a continuous dataset that probes every 5 seconds on average. Why 5 seconds? Because our window size that we've chosen for Ocean is 5 seconds. One thing to note in the graph is that the y-axis ranges from 80 to 100% and not the 0 to 100% for visualization purpose. Now, this naturally brings us to another question. If there's such a huge reduction in the number of probes, would it affect performance? To answer this question, we look at two different things. Firstly, we look at two graphs for a representative user. In this, we see that the blue line corresponds to continuous annotation and the yellow points mark the probe balance due to ocean. We see that these two lines are really close and the ocean framework captures the subtle intraviolent nuances and does not lose a lot of information. But this does not give us a big picture of how the performance is affected. So we have tabulated the minimum, maximum, and the medium values of arousal and valence for both the actual values as well as the sample values. We can clearly see that for almost all the points that most of the values are really close to each other. So this can effectively show that with minimal loss in performance, Ocean can drastically reduce the number of probes needed. Another question that arises is what is the statistics on the number of probes per case dataset? As that's the dataset that you're looking at. As the dataset has three parameters to look at, the number of probes, the videos, and the users. The two graphs over here are with the number of probes averaged across videos and users respectively. We see that on average, the number of probes required is 4 per user and per video. So in this paper, we have introduced Ocean, a novel framework that can be used to annotate emotional data. Ocean detects changes in physiological signals and then uses k-means clustering to decide whether or not to probe for information using k-means. Now we see that the main result produced by our paper is that it reduces the number of probes by 89%, but yet captures similar annotation scores for valence and arousal. Coming to what we will be doing next, we are planning on creating a working prototype for the model and running experiments on live users. This will both validate the framework as well as provide key intuition on how and new insights and challenges that we might face. We also plan on quantifying the storage reduction that happens due to Ocean. We know that Ocean reduces number of probes by 89%. We'd like to see how this pans out in terms of storage state. Another thing that we'd like to see is on the latency of the probing window size. Currently, we need the help of a domain expert to set the window size. And for case, it was 5 seconds. But we would like to look at a way to automate this that should automate this. Another thing that we plan to do is test the framework on other data sets so that we can check the generalizability of the framework. Thank you for your time and attention. If you have any doubts, comments, and suggestions, you can contact me through my email address. Thank you.